Here we are. I think we can start. So I'm very pleased to present you Silvia Pietroni, who was graduated in Rome in La Sapienza, working with black holes in the thesis entitled Hypercritical Neutrino Cooled Accretion onto Black Hole. She did a PhD in Salerno. And I really want you to know that Silvia is also a part of the inclusion in a group called Universe Hall. And maybe she can spend some words speaking about that after the main topic. And yeah, Silvia is going to present you the PhD project she discussed last year, I think, in Salerno. So the stage is yours.
Good morning, thank you everyone. I'm going to talk about the topic of my thesis, that is gravitational lensing by massive exotic objects, which I discussed last year at the University of Salerno. Let's do a brief historical introduction. We know that space-time is curved by the presence of massive bodies, and this curvature influences the motion of the bodies. Okay. I was saying, just a brief historical introduction. We know that space-time is curved by the presence of massive bodies, and the curvature of the space-time influences the motion of the bodies themselves. The main consequence of this curvature is that light, supposed to be massless, bends its trajectory while passing through beside a massive body. So, since the most mysteries of our universe do not show up in observation based on electromagnetic interaction, gravitational lensing is employed in the study of the dark side of the universe. So, the seminar is divided into two main parts. The first part is about weak lensing. The second part is about strong lensing. Regarding the part of weak lensing, I will explain a study about mixed binary systems with potential which decays as 1 over R to the n. And in the second part of the seminar, I will introduce a part regarding the strong lensing, in which I investigated and reconstructed the impact of gravitational lensing in the reconstruction of orbital fits around of some stars orbiting around the Sagittarius A star, which is the supermassive black hole at the center of our galaxy. So regarding the first part about weak lensing, we studied object whose gravitational potential falls as 1 over R to the n, where R is the radial coordinate and n is an index which, when is less than 1, we're talking about ordinary matter. When is greater than 1, we are referring to exotic matter. This kind of potential gives rise to a deflection angle which grows as alpha, which decays like 1 over theta to the n. Theta is the position, the shifted position of the star, because this is a source, this is a massive object, this is the observer. So when the light from the source passes beside a massive body, it's bending. So we don't see the real position of the star, but we see a shifted position. So theta is the angle position in which we observe the source. And n is an index which can represent the ratio between the tangential and the radial pressure in the case of exotic matter, or can represent the halo profile in the case of normal matter. So, which is the astrophysical relevance of this kind of mixed binary lenses? First of all, we say that a mixed binary system is composed by two lenses where the index of the potential is different. So we say the first lens with an index n, the second lens with an index m. The important is in the case in which we investigate a pair of galaxies with different halos. So in the case in which the index n and m is lesser than 1. In the search for wormholes, when these wormholes appear in a non-isolated system. So in the case in which one lens has an index 1 and the second lens has an index 2, because as we said, n equal to 1 is for ordinary matter, while m equal to 2 is for the wormhole. And another interesting channel is in the case when one object is made up of exotic matter and the other one is a normal star. So in the case where n is greater than 1 and m is equal to 1. We refer to a standard lens when we have both indexes equal to 1. And we also used to call this standard case the Schwarzschild case, because we have a Schwarzschild metric for the two objects. So we start from the lens equation of a binary system. Let's say that we have a binary system composed by two lenses. We call it A and B. So we can write the lens equation, where beta is the real source, the real angle position of the source. Theta, as I showed before, is the angle, is shifted angular position, is shifted by the gravitational lensing. Theta is the Einstein radius, and gamma is a parameter called the strength ratio, which is the ratio between the two Einstein radii of the two lenses. Then we make a change of coordinates. We introduce complex coordinates. And at the end, we rewrite the lens equation in this way. Starting from the lens equation, we compute the Jacobian determinant, which is called J. The condition J equal to 0 defines the critical curves on the lens plane. Then we apply the lens map on the critical points of these critical curves, and we find the corresponding points on the source plane. And these points forms the caustics. Caustics are important because when a source crosses a caustic, there is a creation of a couple of images on the corresponding critical points. So the three cases investigated are the case with gamma equal to 1, which is the equal strength binary. The case with gamma equal to the root of 0.1, which is called the unequal strength binary, where the bigger lens is the standard one. By standard, we mean with an index equal to 1, so with a Schwarzschild metric. And then the reverse unequal strength binary, which has the same value of gamma, but it's called reverse because the standard lens is the smaller one in this case. Then we have three topologies according to the separation of the lens, where the separation is the distance between the two lenses. So we have a close separation, an intermediate separation, and a wide separation. And these are the two values of the transition from the close separation to the intermediate separation, from the wide separation to the from the intermediate separation to the wide separation. So we start from the standard binary lenses, so the Schwarzschild case with the two indexes equal to 1. So we have the critical curves here at the top and the corresponding caustics below. Starting from the close case to the wide separation. Starting from these red lines, we can see the caustics evolution. So we decided to keep the first lens with the index equal to 1, and then we varied the index for the second lens in order to study the caustic evolution. So in total, we have 4 parameters. The two indexes n, m, s, which is the separation distance between the two lenses, gamma, which is the parameter, the strength ratio. In this presentation, I will show the equal strength case with gamma equal to 1. So starting from the widest separation, we put the two lenses closer in order to see what happens. And we considered these values for the indexes. So the pink line is for m equal to 0. The blue line is for m equal to 0.5. In these cases, we have, for example, a galactic halo. N equal to 1, as we said, is a Schwarzschild metric, so normal star, black hole. For m equal to 2, the yellow line, we have the Alice wormhole. With m equal to 3, we have exotic matter. So these are the critical curves in the wide separation. These are the corresponding caustics for the wide separation. Then, if we put closer the two lenses, we have the intermediate separation, in which we can see that the critical curves are united, and the same for the caustics. And finally, in the close separation, we have for the critical curves the formation secondary critical curves here in the center. And we have also a singularity, because in the case, only in the case for m equal to 1, we have the appearance of a pseudocaustic. So here we have the two critical curves collapsing on the second lens, and the corresponding caustics remains open over this dashed circle, which is called pseudocaustic. So this pseudocaustic is present only in the case with the index equal to 0. This work was published on Universe in 2020. So this is another, let's say, strange behavior, which is called the elliptic-umbilic catastrophe. And this catastrophe is present only when the range of the index is between 0 and 1. And we were able to recompute exactly at the distance, the separation at which there is this catastrophe. And the behavior is the following. So we have the critical curves, they are becoming smaller, then there is the singularity, then they go up again. And the same is for the caustic. Here is the plot for the transition between the topologies. So here we have the values for gamma, and here we have the values for the separation. So here above we have the values of the separation from the transition to the intermediate to the wide separation, and below we have the values for the transition from the close to the intermediate separation. And in the case of the transition from the close to the intermediate, it was computed only numerically, while the other one was possible to compute it analytically. Then we have another case, which is called the planetary limit. It's called planetary limit because it's the case in which we have one lens much smaller than the other one, in the case of two Schwarzschild objects. In this case, we were able to recompute only in the white case, the extension of the caustics. So the behavior in this planetary limit is this one. We have an extension of the caustic in the parallel and the vertical direction. Which are the possible applications of this kind of simulation? This kind of potential were explored previously by Kitamura, which found out the demagnification effect. The demagnification effect is this signature that it's not present when we have ordinary matter. So this effect may be the evidence of the existence of a wormhole. So we can use this kind of binary lenses in order to find out the existence of exotic matter, for example. And then there is also the implication for the energy momentum tensor supporting this kind of metric. This part was already investigated by Botz and Pietroni, which stated that with an index between 0 and 1, we can have galactic halos. With index greater than 1, we have a signature of violation of the weak energy condition, so the existence of exotic matter. And as I told before, with n equal to 2, we have the Ellis wormhole. So this is regarding the first part on the weak lensing. Regarding the second part of the seminar is the exploration of an application in the case of the strong lensing. So this is done studying the galactic center. We all know that at the center of a galaxy there is a supermassive black hole called Sagittarius A star. And around this black hole there is a cluster of stars called S stars. And among these stars, the most important star is S2, which was important in order to show the existence of the black hole. So, gravity collaboration was able to measure the precession of S2 orbiting around Sagittarius A star. What I did in this part of work is to reconstruct the stellar orbit of S2, S38, and F55. So S2, of course, because is the most studied star around Sagittarius A star, and then S38 and F55 because these are low period stars. So they have a period less than 20 years, so they are suitable for a long time follow-up. So in this paper, we gave an estimation of the impact of gravitational lensing on these stars. So we start from the osculated orbital parameters. These are the real estimated parameters from gravity collaboration. So we have A, which is the semi-major axis, E is the eccentricity of the orbit, E is the inclination of the orbit, omega is the argument of pericenter, omega is the longitude of the ascendental node, T0 is the starting point from which we count the time, the pericenter passage, and P is the period. Then we have also the black hole mass, and D is the distance of the solar system to the galactic center, so the distance from the observer to the black hole. Starting from the Lagrangian, written in Schwarzschild metric, where M is the reduced mass of the star, phi is the true anomaly, R is the radial coordinate, T is the time of the observer at infinity, with the dots we denote the derivative with respect to the proper time tau, and RS is the Schwarzschild radius. Then we write the equation of motion as a function of E and L, where E is the energy and L is the angular momentum, both per unit mass. So we can get the energy and the angular momentum by solving the equation for R dot, evaluating it for R max and R min, which are the apocenter and the pericenter, written as a function of the major axis and the eccentricity. So we have the equation of motion. We solve the equation of motion as in order to find the radial coordinate as a function of tau. and with initial condition, the last center passage and null velocity. And then we get the true anomaly as a function of tau, the proper time as a function of tau from the equation for phi dot t dot. We invert the time, and finally we find r and phi as a function of t, as a function of the time. With these two last one, with these two solutions, we are able to reconstruct with the position. We are able to reconstruct the orbits of these three stars, and with the true anomaly, we are able to recompute the value of the precession of the precession of the stars. And in the case of S2, we find approximately 12 arc minutes, which is a value in agreement with gravity results. Then the light from these stars is deviated by the gravitational field of the black hole. So we indicate with R with S the radial position. We indicate with gamma the angle between the source and the optical axis. So it's the line of sight from the observer to the black hole. The value of gamma is from 0, which represents the perfect alignment of the source behind the lens, so behind the black hole, to pi, and pi is the anti-alignment when we have the source in front of the lens. We rewrite the lens equation in these terms, where delta phi is the azimuthal shift, and R0 is the closest approach. And we solve numerically for R0 in order to find the impact parameter U, and we use the impact parameter to recompute finally theta, which is the real position of the image. In order to quantify the systematic error, so including the gravitational lensing in the reconstruction of this stellar orbit, we perform some iterations with the Gauss-Newton method in order to minimize the chi-square. We starting from a vector theta, which denotes the 7 orbital elements, and then we call delta the shift in the parameters. Then we compare the position, which includes the lensing, with the position without the lensing. By solving this linear equation, we are able to compute the values of delta, which are the shift between the position with lensing and without lensing. J is the Jacobian matrix. And this is the equation in order to compute the chi-square. And the sigma are the statistical uncertainty in each measurement. We use the value of 0.4 millisecond as used in the gravity collaboration. So these are some results for S2. We have the value of gamma, which is the angle between the line of sight and the observer. And here we have the value of the radial coordinate as a function of time. The computation is done on 2 periods. In the middle, we have the variation of the coordinates, so the right ascension and the declination. And here we have the residuals, which are the differences between the values including the lensing and without lensing. So we have a peak when at the very center passage, so when the star is closer to the black hole. We repeat the same computation, the same plots for S38, and then also for S55. These are the values found for gamma, and in the table there are the results for the astrometric shift. So delta, which is put beside the statistical sigma. And the astrometric shift is very small due to the fact that we don't have a perfect alignment, as we can see from the values of the angle gamma. So for S2, we have the shift is 1 order of magnitude below the current uncertainty in the parameters. For S38, S55, we have a less favorable situation because these orbits are closer to face-on orbits, so it means that the orbit is face-on. And the Periastron is not close as the one for S2. So S2 is one of the closest stars to the black hole in this cluster. Then we have the last simulation. We take the real parameters for S2, and we vary the two main parameters affected by the gravitational lensing, which are the semi-major axis and the inclination. So the first simulation is starting from the real value of the semi-major axis, and we reduce the semi-major axis. So basically, we put the star closer to the black hole. And the second simulation is the variation of the inclination angle. So starting from 90 degrees, arriving to this value, this is the real value of the inclination of the orbit, in order to see what happens. So this is the first simulation. We keep the real inclination of the orbit of S2, so it's face-on with respect to the observer, and then we put the star closer to the hole over 2 periods. We can see, so the green line is the one which includes the gravitational lensing, while the red line, which it's not possible to see, it's the orbit unaffected by lensing. So we can see that as much we get closer to the hole, and stronger is the deformation of the orbit. In the second simulation, we start with a reduced semi-major axis, so we are closer to the black hole, with an inclination of 90 degrees. So with an inclination of 90 degrees, it's possible to see the typical deformation, circular deformation of the orbit when an object is closer to the black hole. Then we turn the orbit by 5 degrees to 5 degrees, and we arrive to a face-on inclination. So we can see that the gravitational lensing is stronger when the star is closer to the black hole. These are the plots for the values of delta, which we recomputed before by the linear equation. So we have the values for the shift in the semi-major axis, the shift in the eccentricity, the shift in the inclination, the other angular parameters, and the shift in the period. Here is the original value of the semi-major axis, and here we are closer to the black hole. And we see how this parameter changes. And finally, I show the variation of the p-square. As we can see, it doesn't vary too much. So, to conclude, we estimated that the systematic shift in the orbital elements is 1/10 of the reported uncertainties, and that the astrometric shift caused by the lensing is more prominent when the star is more aligned behind the black hole. And the effect of the lensing is stronger when the star is orbiting closer to the black hole, and when the inclination is closer to edge on orbit, so when it's closer to a 90-degree inclination. And thank you.